So today we will continue with chapter 13 on vibrations and waves. We will see quickly how we can do the derivation for A max, which is omega square A. Then we will apply conservation of mechanical energy that we already know from the chapter on energy to see how we can derive V max and also how to apply this formula for any value of x. So let's start derivation of A max. When there is no friction, summation of forces along the x-axis will be only the tension, and this will be equal to m times A. So T is m times A, okay? And T at the same time is K times X, which is the spring constant times how much compressed or elongated the spring is. Now, I have MA equal Kx. At X equal AX maximum, at X equal X maximum, that is A will be A maximum. So I have A maximum will be K over MA, and K over M is nothing but omega squared. Look at this here, K over M, under the square root, if I do square for both sides, I will get omega squared equal K over M. So A maximum is omega squared times the amplitude. Okay. Now, conservation of mechanical energy. Again, we said in our mass Planck constant, we will be dealing with a situation when there is no friction. So if there is no friction, then the mechanical energy is conserved, which means the mechanical energy at any value x, here I put it in red, at any value x, it's equal to the mechanical energy at x equal x maximum, which is A, right? Okay, what is at any value x? What type of energies I have? At any values x, there is some compression or elongation, so there is EPE, and it is moving to the left or right, so there is kinetic energy. So at any value x, there is kinetic energy plus EPE. However, at x equal to A, the spring stops and then goes back. It stops, it means there is no V, there is no kinetic energy. The only value of energy at x equal A is EPE. Now, what is kinetic energy? It's half mv squared. What is EPE? It's half kx squared. This is equal half ka squared. And we just remove all the halves because it appears in all the equation. I get mv squared plus kx squared equal to ka squared. This is at any value x, okay? Its speed will be related to x via this equation, okay? Now, in the special case, when x equal to 0, when x equal to 0, what will happen to kx squared here? It will disappear, and I will have mv maximum squared equal to ka squared. So, mechanical energy at x equal to A equal EPE at x equal to A equal half ka squared. Mechanical energy at x equal to 0 is kinetic energy at x equal to 0, which is half mv maximum squared. Let's put these two values equal to each other. Half mv maximum squared equal half ka squared. Remove half by half. V maximum squared is k over m a squared. Take the square root of both sides. V maximum is square root of k over m times A. What is square root of k over m? It's omega, and this is why V maximum is omega times A. You just memorize this. V maximum is omega A maximum is omega squared A. But if you want to see where do we get it from, it's from these two derivations. Now, what I want you to keep in mind that not at the particular position x equal x maximum, x equal to 0, x equal minus x maximum, I want you to keep in mind that at any x where it has some v, mv squared plus kx squared equal ka squared. Let's solve this exercise. It's exercise 8, page 44. A 1 kilogram block, so I have the mass equal 1 kilogram, is attached to a spring that has its displacement x as a function of time as shown in the adjacent figure. At time equal to zero, is the mass at rest moving to the positive or moving to the negative? Okay, we have to remember that at time equal to zero, x equal a. So what happens when the spring is maximum elongation? When it is maximum elongation, it is then released from rest. So it's at rest. Okay, part B. Find the time needed by the block to complete one oscillation. Here I have to remember that the time needed to complete one complete oscillation is the period t, okay? And the period t from this graph is 0.2 seconds. Okay, so how did I get it? I come to my graph. The time for one complete, so it's from peak to peak, it's 0.2. The unit is seconds. Okay. Now find the maximum speed of the block. So V maximum, the formula of it is omega times A. So I have to get omega. Let's do omega here. Omega is equal what? Omega is equal to pi f, which is equal to 2 pi f, which is equal to 2 pi divided by the period, which is equal to, if I put 2 times pi divided by 0.2, 31.42. The unit for omega is radian per second. So I got omega. I will plug it here. So V maximum is equal to 31.42. So 31.42 times A. How much is the amplitude of oscillation? I get it from the x-axis. The amplitude of oscillation is 2 times 10 power minus 2. And I get the answer for V maximum to be 0.63 meter per second. Okay, then find the maximum speed and the maximum force. So I have to get the maximum force. The force is the tension. The T maximum will be M A maximum, M times A maximum, which is equal to 1 times A maximum, which is omega squared times A, right? So T maximum is equal to 1 times omega squared is 31.42 squared times A, which is 2 times 10 power minus 2. I get T maximum equal 19.74. Is there another way to get this T maximum? Yes, it's to use, instead of MA maximum, it's to use K times A. So another way to get it is to say T maximum is equal K times X maximum, and X maximum is A. I have to get the K. I get the K from this formula, omega equal square root K over M. I do square both sides, so I get omega squared. So this is omega squared times A. Okay, I have omega from above, and then I get the K, and then I plug it in this equation, and I get my T maximum. Okay, omega squared here, it will be omega squared times M times A. So I can either get it using MA maximum or KA, it should give me the same answer. In the solution down, I used KA, but feel free to use MA maximum. Let's continue. Let's erase this. Part D. Let's do part D here. Use the conservation of mechanical energy to find the speed of the block for x equal -2. So here we will say mechanical energy at x equal A. Always do this. Whenever they say use conservation, or even if they don't say use conservation of mechanical energy, when we have to find the speed at a particular position x, it means I have to use conservation of mechanical energy, where in the equation there is x and v, okay? So I will always start with mechanical energy at x equal A, equal mechanical energy at x equal 10 power minus 2, okay? Now mechanical energy at x equal to A, it is half k A squared, right? This is equal half k x squared plus half mv squared. So half kx at x equal to A, EPE at x equal to A is half ka squared, right? Mechanical energy at x equal 10 power minus 2, it is half kx squared plus half mv squared. Now, this will give me, I can remove all the halves. K, if I didn't bring it in the previous part, I can get it now. K equal omega squared times m. This is equal, omega is 31.42 squared times m. I get K to be 987 Newton per meter. Okay, let's put this in another color just to make it clearer. So here I remove all the K, all the halves. So I'm left with 987 times A, which is 2 to the power 10 power 2 times 10 power minus 2 square is equal to K, which is 987 times X, which is 10 power minus 2 square plus half, the half we get rid of it, plus M, which is 1 times V squared. This is our unknown. We are solving for this value. Okay. So let's solve it. 987 times 2 times 10 power minus 2 to the square is 0.39. This is equal 987 times 10 power minus 2 square. So this is equal 0.098 plus v squared, and I get v squared is equal to 0.292, or v equal 0.54 meter per second. Okay. Okay. Now the last part, at what values of x, the kinetic energy will be equal to the potential energy. So let's make it. So part E, at what? So x equal what? X equal what? The unknown is x, where EPE equal kinetic energy. Okay, so I will be using the same conservation of mechanical energy formula. Mechanical energy at x equal to A equal mechanical energy when EPE is equal to KE. Okay, This will give me, the first side will give me half K A square equal, normally it's EPE plus kinetic energy. But now they're saying EPE equal kinetic energy or kinetic energy equal EPE. So I will put kinetic energy is equal EPE. Okay. Notice I didn't put, I didn't say kinetic energy plus kinetic energy because then I will be solving for V. The question is to find X. So I have to keep here EPE. So I have half K A square equal 2 EPE, which is 2 half K X squared, right? Now I just solve for this. 2 times half is 1. So I have 1 over 2 times K, which is 987, times A, which is 2 times 10 power minus 2 squared equal to K 98. Okay, I can remove the K and the K to make my life easier because I have K here and K here. So this is equal to X, my unknown, squared. Okay, what do I get? I get, let's do on the calculator. So I have 2 times 10 power minus 2 square divided by 2. This is 2 times 10 power minus 4 equal to X squared implies X equal square root both sides 0.014. Okay. So in this exercise, we use the formula omega is equal to 2 pi f. F is 1 over t. Omega is square root of k over m, which gives me, this formula gives me omega square equal km. Okay, this formula is very important. We use it a lot today. Omega square equal km. Okay. We also use the maximum is omega A, and we use A maximum omega square A. We use conservation of mechanical energy to find the position, to find the speed at a particular position X. And we use the conservation of mechanical energy to find the values of X1, the kinetic energy is equal to potential energy. This is a very, very important exercise. That's it for today's lecture. On Monday, we will be solving one more exercise or two, and we'll be finalizing this chapter. So that's it for today. Bye-bye.